So in today's video, I will be explaining the difference between state and pathway functions. This difference is very difficult to understand in some cases, and I will be using a helpful analogy to help some of you finally understand this tough concept. So let's start off with the first part. What exactly do we mean by state? A state can be seen as, let's say, some kind of a snapshot of something. Let's say we take a picture of this person standing in the room, and then something happens and now that person is sitting down. We went from state 1 to state 2. A state is like as if we actually froze time to see something. So in this case, we froze time and we just happened to see this person standing. And in this case, we froze time and we happened to see this person sitting. So it's changed from one state to another state, and that's a state function. It changes from one state to another state to another state to another state. It changes from one instant, right here, one instant in time, one frozen frame of someone's life, to another frozen frame of someone's life. It's like from one state to another state, and that is what a state function can be seen as. For example, the internal energy, which is represented by U, is a known state function. In this case, let's say we take a snapshot of U, and in this case we call it the state U1, and we get this state where there's a lot of U. So let's say it's a high bar right here. And in this case, we take another snapshot of our internal energy. Now we have this lower bar. So it's another state, and we call the state U2. So the internal energy is a state function because it's measured in these instantaneous snapshots. It's either this high U1, lower U2, or let's say a high U3. It's like these instantaneous snapshots of this internal energy. So here we have a lot of internal energy, a little internal energy. It's like these snapshots we took, but in this case we're taking with energy that we actually measured at a certain point in time. So let's say we put the thermometer in the container with U1, in the state of U1, we'll get this much internal energy. And let's say we put a thermometer in another container to measure U2, and we get this much energy. So at this state we have this much U2, at this state we have this much U1. These are like snapshots of how much energy we have. On the other hand, a pathway function is a change in between the two state functions. It's a continuously changing function. So let's say our first state functions, our first instant time, our first state was this person standing up. And our final state was this person sitting down. Well, obviously this person had to go through the sitting down process, the sitting down pathway, in order to go from one state to another state. And that is exactly what I'm illustrating here. In this case, this middle image is going to be our pathway function because it illustrates this person changing from one state to another state. It's literally a moment within his changing position. It shows him changing from one state to another state. However, the problem is if a person's just standing still because he's in a certain state, it's static state, it doesn't change, it's easy to take a photo. It's just this person standing. Or this person sitting. It's also easy to take a photo because the person is sitting as a certain instant in time, and it's like a frozen photo of this person sitting. On the other hand, while the person is sitting down, that process of sitting down, the person is constantly moving during that process. There's no place in that process where he stops because he's on a pathway from one state to another state. And because that person's constantly moving, obviously we're going to have a blurrier picture because that person is moving and the camera obviously has a more difficult time tracking that down. So a state function in this case is like a certain instant time, everything is still, it's a certain snapshot that we can take, it's very easy to see. Meanwhile, a pathway function is something that's constantly changing from one state to another state. Because a state function is like a single state, a pathway function represents a change. It's a constantly changing thing. Therefore, it's difficult to get a snapshot of something that's constantly changing, unlike something that's always in a certain state. Let's say this state or that state. This pathway function to get from one state to another state is constantly changing. It's literally the change itself from state to state. And because the change is always changing, it's difficult to actually get a single snapshot of it. It's constantly changing at every single instant in time. It's never still, so you can take a picture. It's constantly changing. So the picture here is going to be more blurry. You can't really measure it that well. So let's apply it to our studies. Let's use U, which represents internal energy of something, as our state function, and Q, which represents heat, as our pathway function. Now, what does this exactly mean? Well, let's say we wanted to measure U, the U of a substance, the internal energy of a substance. Typically, that's measured with a thermometer. You just stick it in the substance, it has a certain not changing temperature, a certain static temperature, and you can easily measure U. So let's say we measure it and we get U1. Right now, the substance that we measured is at a state. It's in a certain state, in the U1 state, where its internal energy equals U1. That represents that substance single state, let's say. So in that instant, the substance has an internal energy of U1. It's a single state. And then later on, something, let's say we heat up the substance, and then once the temperature stops changing, we measure U2, and we get this other internal energy, which is called U2. So now it's in the U2 state where its internal energy equals to U2. So it changed from the state of U1 to the state of U2, from one internal energy to another internal energy. So let's say here it had a low internal energy, so it was in a low internal energy state, and now it's in a higher internal energy state. These states are measured at a certain instant in time. They're like a static thing. They don't really change, and that is why they're easy to measure. It's like these pictures. Because the person is standing still, he's in a certain state, and therefore it's easy to take a photo of him because he's not moving anywhere. Or here, person sitting still. It's easier to take a photo of that than, let's say, a person moving. And here's the same story. U1 and U2 are in a certain state during a certain instant in time. They're not changing because they're state functions, and therefore they're easy to measure. On the other hand, Q, heat. Heat does not mean energy itself. Heat means energy in a state of change, in a state of transfer, because heat is the transfer of energy from one thing to another thing. And in this case, it means that because the energy is in a state of transfer, it's constantly being transferred. It's not technically a state, it's a pathway, because it's constantly transferring from one thing to another thing. It's literally on a pathway from one thing to another thing constantly. And because it's always being transferred from one thing to another thing, it's constantly changing in value somewhere. So let's say if we were transferring energy to U1, the U in, let's say, from the substance that had U1, it would be constantly changing because we are transferring energy to it constantly. So essentially, Q represents a constant transfer of energy. And you can't really measure a constant transfer of energy because the energy is constantly changing at every single instant in time. You cannot freeze this energy to measure it. The temperature will always be changing, the energy will always be changing, the value of the energy, the value of the internal energy in this case. And because of that, you can't just stick in a thermometer because the thermometer values will be constantly changing. It's like this blurry photo of the person that is always moving. Because it's constantly changing, you can't really measure it. You have to get it to be still. And that is the difference between a pathway function and a state function, because a state wave function is in a certain instant in time. It is still. It is a quantity that can be measured that's not changing. Meanwhile, a pathway function is not still. It's not a state. It's a pathway. It's an always changing thing, an always changing quantity. Like this energy that is always being transferred, constantly being transferred from one thing to another thing. And because it's always being changed, you can't really measure it. You got to wait until it stops changing. It stops being heat and becomes our state again, our internal energy. So until then, you can't measure it. And that's the difference between a pathway function and a state function, because you flow from one state to another state using a certain pathway that's constantly changing along its line. So as a result, you can only, let's say, see one state, and then you can see the next state. You can't see the pathway itself because You can't measure it, I mean, because it's constantly changing and you can't measure constantly changing value. You can only measure the initial state and the final state that are before and after this constantly changing value. So that is why Q, heat, is considered a pathway function, because heat is a flow of energy, it's a constantly changing value, and that is why U, internal energy, is considered a state, because it's a certain energy at one point in time. It's a certain internal energy. It's not this flow, it's not this transfer of energy like Q. Instead, it's like this certain, let's say, assigned quantity at one point and at another point. That's why it's a one state and another state, while Q is a pathway. It's constantly changing, helping this to change from one state to another state, but this Q is constantly changing. Because it's constantly changing, you can't really measure the Q itself because it's constantly changing. It's difficult to see something, to measure something that's always on the move somewhere. This pathway, oh, it's always on the move. And that's the difference between a state function and a pathway function. Now, many people are asking, well, yeah, you can't measure Q, but how do they know Q then? Because in our problems, yes, in our chemistry problems and in our physics problems, we see that Q has a certain value. How is that measured when it's constantly changing and you just said it cannot be measured? Well, it's measured by using the U's at one end and the other end. The difference between U2 and U1 equals Q. You can't measure the Q itself. You can't measure the heat itself. Like literally, you can't stick a thermometer into constantly changing, let's say, energy. It just won't work. The temperature will always be changing and you can't get a single value that you can represent Q as. Instead, you at first measure the initial temperature and then the final temperature, and then you get this difference, and that difference is also equal to Q. But it's not, let's say, it's a difference that represents how the value of Q, but you can't measure Q itself because it's constantly changing. You can't just stick a thermometer into the heat. You only stick a thermometer into a thing that's at a certain internal energy. You can't measure the heat itself literally. You can measure it indirectly by taking the difference of U2 and U1. And that will be delta U, which is then equal to Q in terms of its value. Because we went from U1 to U2 using a certain amount of energy that went from one state to another state. Because this Q, let's say, it flowed into the object that was represented by U1 and changed the object to become U2. And you can't measure the Q itself because it's constantly changing, but you can measure the difference from the initial state to the final state, and that will equal the value of Q that was added to it. So as we can see, we can only measure state functions, but we can't measure pathway functions. We have to take the difference in state functions to find how much this pathway function was initially. Now here's a list of different state and pathway functions. So in this case, our state functions can exist in a certain state. They can be measured at a certain instant in time. For example, something can have a certain enthalpy, H, at a certain instant in time. Something can have a certain internal energy at a certain instant in time that can be measured. Something can have a certain Gibbs free energy at a certain period in time, and this can be easily measured. Something can have a certain entropy. Something can be at a certain pressure and can remain at that pressure. Something in that state. Something can remain at a certain temperature and can remain in that state at that certain temperature. And something can have a certain volume. It can be at a certain volume at that certain state, which has a certain volume. These are all state functions because they represent things that can be in states. You can have a state of a certain enthalpy, of certain internal energy, of a certain Gibbs free energy, of a certain pressure, temperature, volume, entropy. These are things that can be measured in a certain instant. They are literally like the quality something has at a certain period of time that can remain static, can remain still unchanging. They are states. Pathway functions, on the other hand, are these constantly changing processes. You can't measure them like these because they're constantly changing. They are never still. They can never be still. They change the state function from one state to another state And that change from one state to another state, that change itself is the pathway. It's this constantly changing process. And you can't measure the process itself. You can't just stick a thermometer into a process. You can stick a thermometer into a state, you can measure that state, but you can't stick a thermometer into a process because it's constantly changing. You need to wait until a certain state is reached. So, one function, for example, is heat, because heat is a constant flow of energy. It's this process, it's this constantly changing energy. And you can't measure something that's constantly changing. You have to wait until it becomes a state, until it becomes static, unchanging, and then you can measure. For example, you can measure enthalpy, internal energy, Gibbs free energy, entropy, pressure, temperature, and volume, but you can't measure the heat itself. You can't just stick a thermometer into the heat. You can only measure these, let's say, with our thermometer or whatever tool we have. Or work, it's this constantly changing physical state. It's a constantly changing physical movement. It's a constant physical movement. That's what I meant to say. It's a constant physical movement. And you can't really measure constant physical movement that's always going on because it's constantly changing. It's constantly going from one place to another place to another place. You can only measure the final result of it, the final state it reaches. Let's say you move one thing from one state to another thing. Now it's at a different state. It's a different side of the table, let's say. But you can't measure that movement in between itself. You can't just there's no tool that can literally measure per se that movement because it's always changing. You can't get a snapshot of that movement at a certain instant. Instead, you have to wait until it reaches that static state at the end, because the work itself is a process. You can't measure the process itself. You have to measure the initial state and the final state. However, what you can measure from these pathway functions are their values, using our differences in state functions. Let's say we had an initial internal energy of U, then we had a process Q that changed it to a different U. And we can take these differences in U's to find the value of Q. But we can't, because we can measure the initial U and the final U, but we can't measure this Q. We can only only know the value of Q by taking differences in U's. And same, let's say, for work. Let's say we had a certain volume at a certain pressure. That's our state. We can measure the pressure using, let's say, a barometer. We can measure the volume using, let's say, a ruler. These are certain states. They're at a certain state, they're static. And then all of a sudden this process comes along, this constantly changing work process that changes it from one PV to another PV. So now we are at a different pressure and a different volume. It's a different state. And now we can measure this new pressure and this new volume to find the difference between the initial state and the final state. And then that difference will be that work, that the amount of that process that went in. But we can't measure work with any tools. We can't measure work directly. We have to use the difference in pressure and volume to measure this constantly changing value, by how much it changed. But we can't measure this constantly changing value itself because it's constantly changing, and we can't measure something that's constantly changing. We have to wait until it becomes static for us to properly measure it. And these are the lists of state functions and pathway functions, and I hope that from this video you got a better understanding of the difference between state and pathway functions. Feel free to comment any questions or concerns about this video below, and also please subscribe.